Let's now review a concept that we discussed before when we talked about diffusion restriction. We said in summary that diffusion restriction depends on the Brownian motion of signal. And we said typically fluid in the body move in a specific direction, so the vector of signal from movement of fluid is combined, and that gives us the ADC map. When fluid motion is random, the signal from that part protons is cancelled because it's random and it's not going in one direction. When do we have random signal? We have that random signal, for example, in an abscess, where it's filled with fluid, and that fluid is not going anywhere far, rather it's moving in the same place. The signal from those protons cancel each other, and on the ADC map we'll get dark signal. As opposed to CSF signal flow, the CSF particles or protons in the CSF are flowing through the CSF flow gradient or flow direction through the ventricles, out of the ventricles. And so the signal change is combined into a vector and it would be bright on the ADC map. Given that we're interested in the dark signal on the ADC map, we said to get the W diffusion weighted image, we have to invert the ADC map. So anything dark on the ADC map will be bright, and anything bright will be dark, and that's how we get the diffusion weighted images. Now, another concept that we didn't go into too much detail is the b-value. Diffusion weighted images is typically obtained at two b-values, one low and one high. What is b-value? B-value basically determines the amount of signal loss due to Brownian motion. The more there is Brownian motion, or the higher the b-value, the more signal is emitted or ignored due to self-diffusion or due to random motion. Again, let me explain that again. We said the b-value determines the amount of signal loss due to random motion. If we have a very high b-value, we are going to ignore a lot of signal because of self-diffusion, and that's the threshold. That's why we get low b-value and high b-value, and the image final is based on the comparison of those two results. But the higher the b-value determines the amount of signal loss. So higher signal loss, higher b-value leads to higher loss of signal. Now, a question can be asked along the lines of what is the effect of using a high b-value or lower b-value? Now, remember what I said, a higher b-value determines the amount of signal loss that is due to diffusion. So the more or the higher our b-value, the more signal we're going to lose from that. So we do not want to set our b-value or the secondary b-value to be too high because we will increase our noise. So if we obtain image at a higher b-value, then we decrease the signal to noise ratio. Lower b-value will improve the signal to noise, but at the same time, now we'll start considering that that motion is not random and it's intentional and it's going to mix the image. And that's why typically there are two b-values that we use the image for, and one is b-value of 0 or 1,000 or a variation of that number.